Students, today we see different formulas of representation of glucose molecule or any sugar molecule. So, before starting to write down glucose molecule, we can understand how to write down the Fisher projection formula and perspective formula. So, we will take one example, simple example. Suppose glyceraldehyde, CHO, OH, H, CH2OH. This is the simple sugar molecule containing 3 carbon chain, that is triose. Here we can write down the different models. First is the ball and stick model. Ball and stick model. So, how we can write down the ball and stick model? Here the horizontal, it should be look above the plane, OH, and this verticals, it should be below the plane. For example, CHO and CH2OH. So, suppose this is ball and stick model. So, here this group is CHO group. Here this yellow, sorry, if we can take like this. So, this horizontal, they are looking towards us or in above the plane of the paper. So, this is suppose white is aldehyde group, then this CH2OH is red, and this green is OH group, and yellow is H group. So, this is the ball and stick model. We can write down this as it is. The next projection formula is a Fisher projection formula. So, in 19th century, the Emil Fisher introduced this for any asymmetric carbon atom. So, here we can draw the most oxidizable group. So, among all these, the most oxidizable group is aldehyde group. We can write down in vertical line, most of vertical line in the top, and the horizontal bonds which are represent above the plane. So, suppose these are the horizontal bond which are represents above the plane. So, here is the OH, H, and vertical line represents, these bonds represents below the plane. So, this is Fisher projection formulae. Now, another one is the perspective formulae. So, how we can write down this glyceraldehyde into to a perspective formula. So, here we can represent the vertical line or below the plane of the group in dash or dotted. So, like this. So, this is your CHO, this carbon, central carbon, and this is CH2OH, and the group which are pointing towards us or pointing above the plane of the paper, we can show it is as a solid wedge. So, these are OH and H. So, these three are the formulas we can represent any asymmetric compound: ball and stick model, Fisher projection, and perspective model. Now, we will see the configuration. Now, we can represent this configuration into two forms. One is the D and L form, and another one is R and S form. Now, this D and L form, they are relative term of a configuration, relative configuration, and these R and S are absolute configuration. Now, here this D and L, generally we are used for carbohydrates. So, for example, suppose we can take one example, is glyceraldehyde. CHO, OH, CH2OH. Now, here in this Fisher formula of a carbohydrate, the OH group, when it is right hand side, which is near to the CH2OH group, then it is called as D-glyceraldehyde or D configuration. We can draw its mirror image. Here OH group on left hand side. So, it is L-glyceraldehyde. So, only in the right and left terms you consider that OH group which are near to the CH2OH, or it is the last OH group which is attached to this CH2OH carbonate. Now, how we can write down this Fisher form into the perspective form. So, in perspective formula, this vertical you must show dotted CH2OH, and solid horizontal lines you show solid wedges form, that is OHH. Now, if you can look these two, they are exactly mirror image of each other, but this compound A or this structure 1 and structure 2, they are not superimposed on each other. That means these two are non-superimposable mirror image of each other. So, 1 and 2 are non-superimposable mirror images of each other, and therefore this 1 and 2 are enantiomer. So, what is the definition of enantiomers? Enantiomers are the stereoisomers which are non-superimposable mirror images of each other. So, if you understand this D and L, student, this D and L is a relative term. Now, what is now the relative configuration? Relative configuration, the configuration which determined by comparing the configuration of a molecule with that of some arbitrary chosen reference molecule such as D-glyceraldehyde. Now, here this glyceraldehyde molecule is considered as a reference molecule. Now, suppose we can consider one example or one reaction. Now, here we can write down D plus, and we convert this molecule into oxidation, for example bromine and H2O. So, it will form COH, OH, H, CH2OH. So, we will get this D but its specific rotation is change glyceraldehyde. Now in this reaction, the OH group are on the same side, the bond is not broken, but the sign is changed. So the bonds attached to the asymmetric carbon are broken, and this glyceric acid shows the same relative configuration even though its sign of a reaction is different, sign of rotation is different. Here is the plus sign, here is the minus sign. So this relative configuration of a chiral molecules, there is some ambiguity. So this, if we can take the another example, suppose lactic acid or glyceraldehyde on reduction, first we have to reduce it, CH3 OH H CH2OH, and then oxidize, CH3 OH H COOH. So now here this plus D-glyceraldehyde here is again plus 1,2 propanediol, and here plus lactic acid. So in all three reaction, configuration are D and signs are D. In the first reaction, D-glyceraldehyde plus sign get changes to minus sign. Here in D-glyceraldehyde plus sign after reaction remain as it is. So suppose we have an example D glyceric acid and this L plus glyceric lactic acid. We can fix this D and L. So which pronounce dextro and leo, but it is not meaning, these meanings are not always clear. So we are using the different terminology nowadays for a direction of rotation, and that are R and S. So this D-glyceraldehyde we are use as a reference compound not only for the hydroxy but amino acids compounds also, but D and L systems cannot be used all compound containing the chiral center, and therefore the new system, that is R and S, coming into pictures, and these are called as absolute configuration. Absolute configuration. So what is the absolute configuration? Absolute configuration are description which gives arrangements of 4 groups in space attached to the chiral center. Are known as absolute configuration. In this system, the molecule is oriented in such a way that the lowest priority group attached to a chiral is facing away from the observer, or it is at the bottom of the Fisher projection formula, and the remaining group we can write down in a decreasing priority. So suppose we consider glyceraldehyde CHO, OH, CH2OH and H. Now here if we can write down CHO, OH, CH2OH and it is on vertical H. Then this lowest priority group, that is the fourth priority group, is at bottom. First priority group, that is OH group, then second priority group and third priority group. So this is what clockwise direction. So therefore R configuration. Now suppose we can interchange any two group. Here is the OH and CH2OH, CHO and H. So this is the lowest priority group, fourth priority group, first, second, third. Move from first, second to third. So it is anti-clockwise. So this are S configuration. So in absolute configuration, the description which gives the arrangements of four different in space attached to a chiral centers are the absolute configuration. Now we will see the number of stereoisomers according to the asymmetric carbon atom. So configuration of glucose. Configuration of glucose. Here only one chiral carbon present in glyceraldehyde. So total number of isomers are calculated by Ventop's rule. What is Ventop's rule? Ventop's rule are 2 raised to the power n. So what is n? N is the number of asymmetric carbon atom. Suppose in glyceraldehyde there is only one asymmetric carbon atom, then its total number of isomers are 2 raised to the power 1 is equal to 2. So this glyceraldehyde have 2 isomer, D-glyceraldehyde and L-glyceraldehyde. Suppose there are the 2 asymmetric carbons present in sugar molecule. This tetrose. So here 2 chiral carbons are present. So 2 raised to the power 2, n is equal to number of chiral carbon. So total 4. So this tetrose have total 4 optical isomers. Total 4 optical isomer, or you can say the stereo isomers. So which are that stereo isomers? This is one stereo isomers, as this OH group on right hand side which is near to this CH2OH, therefore this is D. This both the OH group are on same side, therefore this is the erythrose. Name of this triose is the erythrose. If you can draw the mirror image of this CHO, OH, OH, CH2, OH. So both OH are on the same side, therefore it is erythrose. and as this OH group on left hand side, therefore it is L erythrols. So this D and L, they are mirror image of each other. So this 1, 2. Then we can draw the structure of 3 O's, one OH from this side, one OH from this side, containing the 4 carbon sugar, that is triose, and mirror image of each CHO, OH, H, OH, CH2OH. So it is 3O. These are again 3 O's. Okay. Here this OH group on left hand side, therefore it is L3Os. This OH group on right hand side, therefore it is D3Os. So this 3 and 4. So if 2 chiral carbon is present in sugar, 2 raised to the power 2 is equal to 4. So total isomers are 4. Now in next we can see the term. We had already seen the enantiomer. Now we will see the diastereomer, then epimer. So to understand all these 3 terms, we will take one example. L glucose, D glucose, then D galactose, then D mannose. Now we will see how to draw this glucose. Now what is the formula of these? All are the hexoses, C6H12O6. So this 6 carbon, 1, 2, 3, 4, 5, 6. Top carbon is aldehyde group, last is CH2OH. Here again CHO, top carbon 2, 3, 4, 5, 6 is again CHO 2, 3, 4, 5, 6. CHO, carbon number 2, carbon number 3, 4, 5 and 6. Now in L-glucose, first we draw the D-glucose structure. So in D-glucose, carbon number 3 having OH left hand side. Then as this is the D-glucose, we can draw 5th number carbon OH on right hand side. These are the right hand side because of D-glucose. Here left hand side because of the L-glucose. Now in D-glucose, only 3rd carbon OH is on left hand side, all carbon or OH on right hand side. So exactly mirror image of D-glucose is L-glucose. So you can draw H, OH on this side, then OH, now the structure of galactose. In galactose, carbon number 2 and carbon number 3, this OH on left hand side, rest all OH on right hand side. In D-mannose, carbon number 3 OH and carbon number 1 OH on right hand side, other all OH on left hand side. So these are the structures of L-glucose, D-glucose, D-galactose and L-mannose. Now what is enantiomer? The non-superimposable mirror images are called as enantiomers. So here if you observe, this L-glucose is exactly the mirror image of D-glucose. Therefore, these two are enantiomer. What is diastereomer? Diastereomer, if you can see, they are not mirror image, not mirror images. So the stereoisomers which are not mirror images of each other are called as diastereomer. So glucose and galactose, they are diastereomers of each other. Now we will see the epimer. What is epimer? Now epimer are the orientation of OH must differ only at one place or one carbon place. Okay. Now if you can observe, in glucose and in galactose, so here carbon number 4, this is carbon number 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So if you can observe carbon number 4, so carbon number 2 same orientation, carbon number 3 same orientation, carbon number 5 same orientation, only the orientation at one carbon atom is changed, and therefore glucose and galactose are C4 epimer, because at C4 these are orientation of a OH are changed. Now if you can see,